5.4 Indefinite integrals and the net change theorem. What is the net change theorem? In our study of the fundamental theorem, we arrived at a way to find the antiderivative of the area accumulation function. Now, this was a particular antiderivative. We would like to now find a convenient notation for antiderivatives in general. And this is the indefinite integral notation that we're now going to use. It's just the integral symbol without the limits of integration, which means to find the antiderivative. That'll be capital F of x. We know we have an antiderivative if when we take its derivative, we get back to the function. Putting a plus c means that represents the entire family of functions, where no c means we're just finding one particular one that matches that situation. We want to distinguish between definite and indefinite integrals. And again, when you put the limits of integration, that gives us a number, where when you don't put the limits of integration, it represents the family of functions. So this is a definite integral because of the limits of integration. This is a indefinite integral, and it provides the family of antiderivatives. We want to find the general indefinite integral for this, and we can use some of our properties by the integral of the sum is the sum of the integrals, so we can find the integral of each portion of the expression, and at the end again put plus c, and this again represents the family of antiderivatives. It's your turn. Go ahead and stop the screencast and see if you can find the indefinite integral for these 4 examples. Here are the answers. Let's take a look at evaluating this indefinite integral. It looks kind of daunting right here until we use a little bit of algebra and go ahead and rewrite it in a different form. So we're going to take that sine squared of theta, split it up, and we're going to have 2 factors being multiplied. This factor can be rewritten, this factor can be rewritten, and hopefully that looks like a derivative answer that we have done in the past. So going backwards, the answer would be negative cosecant theta plus c. Now this is a definite integral. It's going to yield a number. We're going to find the antiderivative of each and evaluate from 0 to 3, and we're going to get our net change. Your turn. Go ahead and try to find the indefinite integral for these 4 problems. And here are the answers. You can see that I had to manipulate by distributing here, and then I was able to see expressions that I knew the antiderivative of. Here I had to use a identity, and once I used the identity, I was able to reduce and get a simpler form in which I was able to do that. Here, hopefully you recognize the identity, and again, you can proceed from there. Here is a definite integral, and we want to interpret the results in terms of area. So we go ahead and find the antiderivative of each, evaluate, and this is the exact answer. And if you put it in the calculator, you're going to get a negative result, which means that when the area accumulator was adding up all the areas, it was below the x-axis and above the x-axis, and it looks like there was more area below the x-axis than there was above. The fundamental theorem again is a net result, and it utilizes the antiderivative evaluate the upper limit minus the antiderivative evaluate the lower limit. Instead of writing f of x, I'm going to write its derivative, which should remind you that we are finding area under a rate of change. And so this, finding the area under a rate of change, is what we call net change, where we allow the negative and positive areas to cancel each other out. Here's an example of finding the area under velocity, and there's 2 parts, part A and part B. Part A is asking us to find the displacement. In other words, we are going to allow the negative areas and positive areas to cancel out, and we get this result, which is negative 4.5. So this tells me there was probably more area between the curve and the x-axis underneath than there was above. Now the net result is that the location or the location of the object was negative 4.5 or 4.5 meters to the left of its original starting point. Now let's go to part B. Part B is to find the distance traveled, which means we have to look at the curve now. We suspected there was area underneath the x-axis and area above the x-axis. What we're going to do is we're going to separate these two. We know that the 0 is at 3, and we're going to separate the two integrals. Knowing that this result is going to be negative, I'm going to put a negative sign in here to force this to be a positive result. This is already going to be a positive result because the heights are positive and the widths are positive. And we're going to get the answer here. And this determines the total distance traveled. So I suspect what the particle did was go to the left and then go to the right and not all the way to the place where it started. But we count this distance and this distance. Okay, your turn. Again, you need to find two things. You need to find the displacement and you need to find the distance traveled. Go ahead and stop the screencast and see what you can do. A graph of the function might be helpful. And here is the answer. 57 was just the part A was just to find the definite integral, and that would be net change. But to get part B, I had to actually provide a graph, and I saw that I had negative area from 0 to 5/3. So I went ahead and made the velocity equal to 0 so I can find when it crossed. And then I'm going to have positive area. So knowing that the first integral was going to be negative, I preceded it by a minus sign, and then the second integral was going to be positive. Now I didn't evaluate, I'll let you do that. 58 is done in the same way. One of the tips that I can give you, if you know the integral is going to be negative, instead of just putting a negative in front, you can just easily just put the absolute value. And that forces that outcome to be positive. Okay, let's take a look at the representation in units of this. Remember, this is the area under a rate of change. And in this particular problem, the rate of change is pounds per year. So if you're trying to find the area under a rate of change of pounds per year, you'll be just getting the total pounds for year 5 to 10. I'd like you to try to do the rest of the problems. Stop the screencast and see what you can do. And these are the answers to the remaining problems.